In this video, we're going to look at a few more examples of combining our power series or using the tools of differentiation and integration in order to create new power series. So for our first example, I want to find the power series representation for the function g of x equals negative 1 over 1 plus x squared centered at 0 by either differentiating or integrating the power series for f of x equals 1 over 1 plus x. So I'm trying to find the power series for this g using a known power series for f. And it looks like the tool I'm going to want to use is going to be differentiating, since I see that when I have that 1 over 1 plus x, taking its derivative, I will end up with that negative 1 over 1 plus x squared. So the first thing that we need to do is get a power series for f of x. So notice that f of x is 1 over 1 plus x, which I could write as 1 over 1 minus negative x. So recall that we know that 1 over 1 minus x equals the sum from k equals 0 to infinity of x to the k for the absolute value of x less than 1. Now, you're not expected to memorize these various power series. If we want you to manipulate a power series, we'll give you a starting power series for a problem. So we have that as our starting power series. 1 over 1 plus x can equal 1 over 1 minus negative x. So that power series will be the sum from k equals 0 to infinity of negative x to the k, and that would converge for absolute value of negative x less than 1, which will end up with the same interval of convergence as before. Okay, so I have a power series now. I can also, when I'm going to do something else with it, like take its derivative, it's going to help me to write this as a sum of some constant terms and then power terms. So I'm going to write that as a sum of negative 1 to the k times x to the k, since in my next step I'm actually going to have to differentiate that power series. Okay, so the next step is now take the derivative. Okay, well, we want to note that the derivative of 1 over 1 plus x is equal to negative 1 over 1 plus x squared, okay, which is the function that I'm trying to find a power series representation for. So negative 1 over 1 plus x squared being equal to the derivative of 1 over 1 plus x will equal the derivative of the power series representation of 1 over 1 plus x. So the derivative of the sum from k equals 0 to infinity of negative 1 to the k x to the k. So I can do my term by term differentiation. So I'm going to have a sum from k equals 0 to infinity of this negative 1 to the k. So this is what we treat as a constant because it doesn't have any x's in it. And then times my power derivative rule. So I'm going to have k times x to the k minus 1. And again, notice that when I would plug in k equals 0, I would get 0 for the first term. So I can choose to re-index this and have k start at 1, and then have negative 1 to the k times k x to the k minus 1. Okay, notice that this will also be converging for the absolute value of x less than 1. The radius of convergence we know is still going to be r equals 1, and I notice that if I would plug in 1 or negative 1 into this, I'm just going to end up with either a sum of k or a sum of some negative 1 to some sort of k power times k. So in both cases it would diverge, like we saw in a previous example. Okay, so we have a power series representation then for negative 1 over 1 plus x squared. So let's look at just 2 more examples here to get some more power series for functions. What we're seeing here is how these tools of combining power series, taking derivatives of power series, integrals of power series, allows us to create a lot more power series representations for different functions. So for our next example, we're reminded that we earlier found a power series representation for 1 over 1 plus x squared. So that's going to be what we're going to want to start with here. So earlier in the notes, we found that 1 over 1 plus x squared was equal to a sum from k equals 0 to infinity of negative 1 to the k x to the 2k for the absolute value of x less than 1. Now we want to use that power series to find a power series representation centered at 0 for the arctan function, or the inverse tan function, and then give the interval of convergence for that series. So what's the relationship between 1 over 1 plus x squared and the inverse tan function? Well, we know that the integral of 1 over 1 plus x squared dx is equal to tan inverse of x plus c. So I want to integrate this power series representation to get a power series representation for tan inverse x. Remember, I often will use both notations. Tan inverse x is the same thing as arctan x. Okay. So taking the integral of both sides here, I'll have the integral of 1 over 1 plus x squared is my tan inverse x. I guess I'll go ahead and use that notation here. This is equal to an integral then of this sum from k equals 0 to infinity, negative 1 to the k, x to the 2k dx, okay, which is equal to a sum from k equals 0 to infinity. This negative 1 to the k here is like a constant term. So I have negative 1 to the k, and then I'm going to have my power antiderivative rule on that x to the 2k. So that's x to some quantity, that 2k quantity. So I'm going to have x to the 2k plus 1. We just add 1 to whatever our power is, and then I'll have that divided by 2k plus 1. Okay, and then I'll have that plus c. So I've got this inverse tangent is equal to this sum plus c. Now this is again true for all x, so we can solve for our c by plugging in one particular value of x. Let's say we'll plug in x equals 0. So I'll have tan inverse of 0 is equal to 0 plus c. I know that tan inverse of 0 is 0. So I end up with c equals 0. Okay, so I've got my tan inverse x equals this sum from k equals 0 to infinity of negative 1 to the k, x to the 2k plus 1, all over 2k plus 1. Okay. Notice the series that I was taking the integral of had a radius of convergence of 1. So my radius of convergence will still be 1. I'm centered at a equals 0. So I just have to test what happens at those endpoints of negative 1 and 1. Okay, so let's look at what happens at negative 1. When x equals negative 1, I'll have a sum from k equals 0 to infinity of negative 1 to the k times negative 1 to the 2k plus 1 all over 2k plus 1. So let's simplify this. This is going to be equal to the sum from k equals 0 to infinity. This negative 1 to the 2k plus 1, that's like negative 1 to the 2k times negative 1. And negative 1 to the 2k would just it'd be an even power of negative 1, so that would always be positive. So I'm just going to be left with the negative 1 to the k and the negative 1 to the 1. So I can rewrite this as negative 1 to the k plus 1 all over 2k plus 1. Okay, so without going through all of the details, we'll just sort of talk out why, what the convergence is of this particular sum here. Notice that this is going to be an alternating series here. That looks rather similar to the alternating harmonic series. We could end up showing that this converges by our alternating series test. The limit of the magnitude of those terms goes to 0, and we could show that those terms, the magnitude of the terms is decreasing as well. Okay, so we're not going through the full details at the moment, but we can show that that converges. So let's also look at what happens at x equals 1. So we'll just sort of go down here because we're running out a little bit of room. So at x equals 1, I would have a sum from k equals 0 to infinity of negative 1 to the k times 1 to the 2k plus 1, so that'll just be 1 all over 2k plus 1. Again, we can show that this converges by the alternating series test. So when I would go to state what my interval of convergence is, I'm going to have my interval be from negative 1 to 1. So now let's look at our last example here. Now I want to use this series that I just found for arctan x to find a power series representation centered at 0 for the function tan inverse of 4x squared. So we've just done an example of using the derivative, term-by-term differentiation of a power series to get a new power series. We did the term-by-term integration to get a new power series. And then we're back again to doing one of those other kinds of manipulations with a composition of series. So just seeing how all of these tools together help us create power series for a wide range of functions. So I want the power series here for this inverse tangent of 4x squared. So we have tan inverse of 4x squared equals the sum from k equals 0 to infinity, negative 1 to the k, our 4x squared to the 2k plus 1, all over 2k plus 1. And since our inverse tangent function had this interval of convergence for x between negative 1 and 1, including those endpoints, when I have this substitution of 4x squared in for x, this will be for that 4x squared being less than or equal to 1. So I'll have x squared is less than or equal to 1/4, which will mean my x will be between negative a half and a half, including those different endpoints. That will be my interval of convergence here. Okay. It could also be useful for me to rewrite this series a little bit. So let me just go down one more line and say tan inverse of 4x squared here is equal to the sum from k equals 0 to infinity of negative 1 to the k, 4 to the 2k plus 1, and then x to the 4k plus 2 all over 2k plus 1. So I have that where my interval of convergence again is this absolute value of x is less than or equal to a half, or that x is between negative a half and 1/2. So this would be our final answer here. I'll just point out that it's going to be useful for us to rewrite our terms often in this way, where I have all of these pieces here are my constant term, and then I have the power of x written as one single thing. So I can identify these terms here as my coefficients, okay, and then I have my power of x. So if I wanted to do anything else with that, differentiate or integrate, I clearly have it separated into the coefficient term and then the power of x term.